Hey, what's up, guys? This is Cheng here. So this time, 1786, number of restricted paths from first to last node. Okay, so you're given like an undirected, weighted connected graph here, and which is like represented by an n, which is the number of nodes, and a bunch of edges with weight on it, right? So and the path, right? So a path from start to end is a sequence of nodes, right? So here's just like definition of path here. And so the distance of a path, is the sum of the weights on the edges of the path, okay, right? And then so we're defining like a distance to last node, x. So this one means that the current node x, the shortest distance between the x and the n, right? So n basically is the last node, right? That's the definition of this function here. And then another one is that we define like a restricted path here. So a restricted path is the basically it so the distance of each node, right, to the last between the current between each node to the last node is in the decreasing sequence here. Okay, and then lastly, it asks you to return the number of restricted paths from node 1 to n. Remember, it's from 1 to n. We're only calculating the restricted path from the starting node to the end node, right? So and here's an example here. So first thing is obviously we need to calculate the basically the shortest path, right, between all the nodes and the the nodes n here, which is 5, right? So here we have like so of course 5, the distance between 5 and 5 is 0, right? And then between the distance between 2 and 5 is 2, and then between 1 and 5 is 4, between 4 and 5 is 6, right? So on and so forth. And then the once we have the shortest distance, right, between each node and to the last node here, we can find the restricted path, right? So like I said, the restricted path is that the distance, right, has to be in the decreasing order, which means that in our case we have 3 paths here. The first one is this one. The first one, since it's always going to be from n from 1 to n, right? That's why from 1, starting from 1, it can go to 2, and from 2, sorry, 1 to 2, and from 2 we have 2 options here. We can either go to 5 directly, or we can go to 3, 5, and another one, the last one is we from 1, 3, and 5, because they're all like in the decreasing order. Right, cool. And then we have this kind of like constraints here, right? So we have this kind of almost 10 to the power of 5. Right. So I mean, to solve this problem, I think it's obvious that we need to first calculate the shortest distance, right, between each node to the last node, which means that we have to use a Dijkstrand, right, algorithm to do that. And after calculating that one, I think the rest will be simple, like a DP problem, right, from 1 to n. Basically, from the current one, we enumerate to each of the neighbors. As long as the neighbor has the distance, right, smaller than the current one, then we can just continue doing it until we have reached the last one, right? As long as we can reach the last node, which is 5 here, and then we know, okay, we find a path. That's when we'll return 1 there. Cool. So I think it's pretty clear, right? So the first step is that we have to calculate the shortest distance. So which means that we're gonna build a graph here. So I'm gonna default a dictionary here. So we have a list, right? And then to build the graph, we have this U, V, and W, right, in edges. Then the graph of U dot append V and W, right? Since we need to build the undirected graph here, append U and W, right? So for the shortest distance, okay, I call it shortest distance. At the beginning, everyone is max size, okay, n+1 for each of the nodes. And the reason I do n+1 is because because the node is one based, right? That's why we have to do n+1. And shortest distance like 0, right? That's not 0. In this case, it's n, right? Because we're starting from this last node, right? This one equals to 0. Then we have a sin equals to set, and then we're gonna use a priority queue, right? So at the beginning, it's gonna be the current distance, which is 0, and the node is n, right? While priority queue, we have kind of the current distance, and we have the current node, right? It's gonna be a heap queue dot heap pop, then priority queue, and then we add this one to the scene, right? So this is just like a diagonal template. If you guys don't know what diagonal algorithm is, I think you can easily find a lot of like explanations online that can tell you what this algorithm is doing, right? Basically, for each neighbors, right, in the graph of current, we first check if the neighbor has not been seen before, not in scene, and then we have the new distance, right? So I call it new distance. So the new distance will be the distance plus the current weight, right? And then if the new distance is smaller than the shortest distance of the current neighbors, then we know we find a better answer, find a shorter distance for this kind of neighbor, right? Now we can just push this one into the priority queue, right? With the new distance plus the neighbor, right? And then we also update the shortest distance, right, with this new distance, right? And basically after this while loop here, we're gonna have the shortest distance for each of the nodes stored in this array here. Okay, and then the next one is just like we just need to do basically the DFS, right, or a top-down DP to calculate the path from 1 to n. So which means I'm going to use basically a DP of 1 here, and then in the end we have mod equals to 10 to the power of 9 plus 7, return answer mod, do a modular, right? And so the last part is to implement DP function, right? LRU cache none, right? I mean, for this kind of DP, I think it's kind of obvious that we simply need to do like a DFS, right? From 1 to 5, and every time we have answer equals to 0. Basically, every time we check the neighbors, right? We check the neighbors and the weight, in graph the current one, if the shortest one, if the current distance is greater than the neighbor distance, we know that okay, this path is a valid path, right? So basically, this DP, what we're defining here is that that's going to be the total path, right? The total restricted path starting from the current node and end with the last node. That's going to be the definition of the DP here. So every time when we at the current node here, we check all the neighbors, and then we do this one, right? And if this one, if the current distance is greater than the neighbor, and then we know we can go to that path, which means that we're gonna do an answer, accumulate that one to neighbor, and then in the end we return the answer. So the reason we can do the accumulates dp is because, you know, if the current one is equal to n, which means that we have reached the last node, then we know, okay, we find a path, which means we're gonna return 1 here, right? And so one more thing here is, you know, I didn't check the duplication here. Basically, you know, let's say we are starting from 1, we reach 2 here, right? From 1 we reach 2 here. But when we add 2 here, you know, 2 has like neighbors, right? Has 3 neighbors, which is 3, 5, and 1, which means that in this for loop here, it will also check 1 here. So the reason I didn't maintain like a scene set is because this one will always be false whenever we check the current one with its parents, right? Because if we add a 2 here, you know, basically the neighbors, in this case the neighbor which is 1, the distance will always be greater than the current one. That's why, you know, we'll never go back to the node we have ever visited before, because of this if check here. Okay. All right, I think that's it is. And if I want to run this one, let's see. Shortest. Okay, I think there's a typo here. Accept it. Yeah, so it's passed, right? Let's see what else. And regarding the time complexity, right? So, I mean, for the Dijkstra algorithm, the time complexity for Dijkstra algorithm is the number of edges times log the numbers of vertices. That's the time complexity for that Dijkstra. And then for this kind of DP here, you know, it's actually, so obviously it's like O of n, right? So so n is the node, the current node is v, right? Number of v times times the neighbors, right? The neighbor of that node. So it's going to be a v times yeah, because I would say this one is like kind of of 1 here, because, you know, one node, yes, it could have like up to n neighbors, but on average, I would say it should be like a limited number of neighbors. So I would say this. So for the DP, I think the time complexity is close to O of v here. So I think the total time complexity is going to be a e times log v plus O of v. Yeah. Yeah, I think that's it, right? So this one, I think it's kind of straightforward. Basically, the first step is that we use the Dijkstra algorithm to calculate the shortest distance for each node, between each node and the last node. Okay, and once we have that information, so we can just utilize a simple DP solution here to calculate the total restricted path, right? Given like by using this kind of a constraint here, right? Yeah, cool. I think I would stop here, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.